Okay, good afternoon, everyone, and thanks for coming from the snowstorm. Hopefully, this is the last snow before we see the real spring and the summer. Okay, so first thing, we won't have quiz this week as well, because the next quiz will cover about some basic statistics, correlation coefficient, and some like unbiased estimate, which is gonna covered until we finish the two lectures. So we decided to not put the quiz ahead of our schedule. Okay. And then yeah, if you have now started doing like homework 5, please spend some time doing that. And because next Tuesday will be the due of homework 5, and then the release will homework 6, which will be our last homework assignment. And because of the tight schedule for the end of the semester, like including, I believe every one of you have is taking multiple courses, right? So there will be pretty tight schedule. And also the administration will ask us to submit the final grade by some deadline, which is pretty tight as well. So that means like we won't be able to make extension or give like arbitrary long personal extension. That's not possible. Yeah, so if you could start doing those things on time, that won't affect your final grade. That will be kind of win-win, right? Will be good for you and will be good for us. Okay. Okay, so today we're gonna wrap up the correlation coefficient stuff which we discussed at end of last lecture. Then we're gonna introduce in some basic concepts in statistics. We're gonna introduce what does it mean for statistics. Okay, so the correlation, this concept is motivated by the definition of the covariance. So that was the main topic throughout the previous lecture, the last lecture. So the covariance, I'm gonna write down the definition here. Right? So we know the covariance has two definitions. The original definition is an expectation of a function of two random variables. Okay? So it is the multiplication of two random variables centralized by their expectations. Okay. So see, x subtracted by expectation of x, this is called centralization. And y is subtracted by expectation of y, and then we'll multiply them together. And then we'll take expectation, right? So the covariance indicates how much, in which kind of direction and in which kind of like degree the two variables, two random variables are changing. If they're changing along the opposite direction, then covariance is negative. If they're changing along the same direction, the covariance is positive. And the value, the magnitude of covariance indicates how much strong they're changing together, right? If the covariance is very big, meaning that when one variable changes much, the other variable changes as much as well, right? And otherwise, the covariance, this very small covariance indicates that when one variable changes very much, but the other variables might change later. And we have some like conclusions. First, if two random variables are independent, then how about their covariance? What's the value of the covariance if the two random variables are independent to each other? Any thought? Yes, exactly, right? This is very, very important conclusion, please keep it in mind. And you can also show that from the definition. Right? So if two random variables are independent to each other, from the definition, you can show that the covariance is simply 0. Now, if we change the statement in the opposite direction, is that true? Namely, could we say if the covariance of x, y is 0, x and y are independent to each other? No, right? Because the covariance is actually represents a kind of like linear dependencies. So you can now say if the two random variables are independent to each other, meaning that they're independent in any sense, right? Arbitrary sense. So the covariance must be 0. But the covariance being 0 just exclude one possible this dependency relationship between two random variables. It doesn't exclude all. So that means you can now say, okay, x, y are independent to each other. So so basically it's a sufficient condition. It's not a necessary condition. And if we can leverage the definition, the original definition of the covariance, you can further simplify it to the second definition, which might be easier to memorize. So the covariance can be also defined as the expectation of the product subtracted by the product of the expectation. Again, please try to replicate the proof we show in the class by yourself, because it includes a very important trick. You expand those terms and then apply the linearity of the expectation, and you'll find that some terms are canceled, some terms are preserved, and eventually you will get this. Okay. So although covariance is useful and important, but in practice it has some issue, as we discussed in the previous in the last lecture, right? So if I multiply x, say by 10, multiply y by 10, then the covariance will be amplified by 100. Right? We can verify by ourselves, right? So if you just calculate covariance of 10x, 10y, you will see that probably you can leverage this definition, right? You can immediately obtain that the covariance will be 100 times the covariance between x and y. Right? So that is actually not very intuitive. So in practice, especially statistical experiments, we want to say, okay, I want to compare how much correlated between different pairs of random variables, right? So if x and y, we know its covariance is 0.5, say, and even they are both multiplied by some factor, the covariance, some kind of correlation measurement should be invariant, right? Should be still 0.5 rather than 50. Then we don't need to worry about the scaling issues. So that means like the covariance definition has some issue, right? It is not skew invariant. That motivates the definition of the so-called correlation or correlation coefficient. So what is correlation coefficient? You just normalize the covariance by the product of the standard deviations of these two random variables. Right? So variance takes square root is standard deviation, right? So you divide the covariance of x and y by the standard deviation of x and standard deviation of y, you got your correlation. Any question regarding definition? What's the benefit? The benefit is that when you use correlation or correlation coefficient rho to measure the dependencies between two random variables, they're not varying by some scalars. Like say, if you multiply x by some constant factor r, you multiply y by some constant factor s, their correlation is exactly the same as the correlation between x and y. Okay. So it's completely skew invariant. Of course, you need to make sure r and s are non-zero, right? Question? Okay. So correlation is a skew-free measure of dependencies. That's why in practice, when we compare pairs of the random variables in terms of their dependencies, people usually use the so-called correlation or correlation coefficient. And one example is the definition of the so-called bivariate Gaussian distribution. So previously we introduced the Gaussian distribution, right? So if x follows a so-called Gaussian distribution parameterized by this mean parameter mu x and standard deviation parameter sigma x, that means the PDF of x, let me write it in this way, will take a special form. Okay. Let me just write it down, right? I hope you guys have memorized this, right? So it is square root 2 pi times standard deviation times exponential and 1 over 2 sigma x squared and x minus mu x squared. So this is the form of the probability density function for the Gaussian random variable, right, which we have seen many, many times, right? So two parameters, mu x and sigma x, which tells us that if you use this Gaussian CDF, then the expectation of x will be just mu x. And the variance of x will be just sigma x squared. Okay. And similarly, if y follows the Gaussian distribution, its PDF follows the same form. Here, let me just write it out. Sigma y times exponential to the power 1 over sigma y squared y minus mu y squared. Okay. Any question at this point? We're just quickly reviewing what we have, just quickly recalling what we have discussed before. Okay, so if these two Gaussian random variables, say x, y, are independent, then what is their joint probability density function? What is the joint PDF of x and y? What? Y is 0. Oh, we're talking about the joint probability density function, not the covariance. Yeah, the covariance, of course, is 0, right? So here we're talking about the joint PDF. So what's the form of the joint PDF? Any thought? Yeah, we should think about the properties about the joint PDF and marginal PDF we have discussed previously, right? So if two random variables are independent to each other, their joint PDF can be decomposed as what? Any thought? Yes, exactly right. We just leverage this fact, right? So if X, Y are independent to each other, that basically says their joint PDF is just the product of their respective single variables PDF, right? So it is just fx of x times fy, right? So just multiply these two guys together. So the multiplication will give you this form, right? So it's pretty straightforward because when you multiply two exponential term, you just need to add up. You just need to add up the exponents, right? And these two factors, when you multiply together, square root will cancel, and you got 2 pi here, you got sigma x times sigma y, and you merge the exponents, you got the joint density function for x and y. Okay, so that's a straightforward case. But when x and y are dependent, what will be the joint density look like? In a Gaussian distribution, if x, y are dependent, then their joint PDF will be characterized by the correlation coefficient. So this is the general form, correlated case, where x and y are dependent. And suppose their correlation is rho. Then the joint density takes this form. Right? So you don't need to memorize this, right? Just to give you a sense, okay, when the two Gaussian random variables are dependent and you know their correlation coefficient, then you can directly write down the joint PDF in this form, right? And you can open up, you can use our slide as reference as a dictionary to retrieve, right? Retrieve it, right? So you see that the factor, you still have 1 over 2 pi, then sigma x times sigma y, but now you're gonna multiply a factor square root of 1 minus sigma square, 1 minus rho square. In exponent, you see here, you got 1 over 2 times this 1 minus rho square. And then you have 3 terms here. The first one is still x minus mu x squared over sigma x squared. The second one is y minus mu y squared over sigma y squared. And third one is you're going to subtract this summation by minus 2 times rho, and then this cross product, x minus mu x, y minus mu y, and then divided by sigma x sigma. So this is the general form. So we can verify that. What will happen if x, y are independent? If x and y are independent, what's the value of rho? What's the value of rho if x, y are independent to each other? Rho is the correlation. Yes, it's 0, right? Rho is 0, then you see that this guy will becomes 1, right? And this guy will become 1. You're gonna have it's canceled, you have this canceled, not canceled. I wouldn't say come, it's just disappear, it's constant 1, right? And this guy, because rho is 0, and this term is 0 as well. So you see that you're gonna recover the simpler case where x, y are independent. Okay, any question regarding the general form of the bivariate Gaussian distribution as PDF? Okay, again, you don't need to memorize that, but just you need to realize that when two Gaussian random variables, they are dependent, then the joint PDF will have to include the correlation coefficient. Okay. So here's a summary. So we introduced the definition of the covariance, which represents a particular type of dependencies between random variables. You can calculate as the expectation of the product of the random variables subtracted by the product of the expectation of random variables. And this covariance, however, is not skew invariant. That means whenever you skew x and y by some factor, your covariance will change. To address this issue, we normalize the covariance by the product of the standard deviations of each individual random variable. We get this correlation rule, which is in skew invariant. And also, we see an important property of the variance. So we know that for expectation, right, linear combination of random variables are, and then take expectation is the linear combination of the expectation. Right? This is called the linearity of the expectation. But for variance, it doesn't have such linearity. We give a simplest case where if you look at the variance of x plus y, it is actually the variance of x plus the variance y plus 2 times the covariance of x, y. Right? You have to include the covariance between the two random variables. Questions? Okay. Okay, so now let us start talking about some basic concepts in statistics. So, so far, we talked about single random variable. A single random variable has probability density functions and cumulative density functions, right? And then we talk about the relationship between two random variables. So if you look into the relationship between the two random variables, we are interested in what is their joint probability density function, right? What's the relationship between the joint density and the marginal densities? Of course, if x, y are independent to each other, then joint density should be decomposed as the product marginal densities, or the conditional densities should be the same as marginal densities, and so on. But those are all about two random variables. And in general, we want to extend our investigation to multiple random variables, not just two. Like consider we have n random variables, x1 through xn. Right? This n could be very large. Say n is 100 or 1000. Right? And in such cases, it's really very, very hard to write down a joint probability density function of their of all x1 through xn. Or it's very hard to compute what is the conditional density and so on. So that motivates us to define some so-called statistics over this set of random variables and look at what does the statistics, what's the value of the statistics and what's the property of the statistics to represent some kind of common underlying properties reflect by this set of random variables. That is so-called statistics. And the discipline, which is called statistics, are mostly talking about this. How do we construct effective statistics over a set of random variables? Maybe this set of random variables is pretty large, right? It's pretty many. I mean, and then if you can define some statistics over this set of random variables, and what's the value range of those statistics can reflect some properties, some underlying properties behind or within this set of random variables. Okay, that's the motivation. So we're gonna start with a very simple setting where we assume this set of random variables are independent and identically distributed. So that means I have a x1, x2 through xn, right? N can be arbitrarily large. We say these n random variables are independent and identically distributed. Usually this is abbreviated as RID. If these n random variables share the same probability distribution and are independent of each other. In other words, if we want to write down the joint probability density function of these n random variables, it will be simply the product of the marginal probability density function of each individual random variables. Then, and also, all the marginal density functions are identical, are exactly the same form. Then we say x1 through xn are RID. That's why when you say many statistical literature textbooks, they say, okay, assume a set of RID random variables. This is a word, this term, this short name RID comes from. Question regarding definition? Okay. So now imagine we want to do some random experiments now, right? And suppose I have the mechanism to repeatedly doing the same experiment independently, say for n times. The simplest example might be flip the coin, right? Suppose I have a coin in my hand. I don't know what's the chance that you see the heads up or see the tail up, right? I just keep flipping my experiment, flipping my coin, right? And I make sure that every time when I flip my coin, my muscle, my body, my throwing, my flipping action has nothing to do with my previous body status. So I can make sure the outcomes of each experiment are independent. Okay. Suppose I have collected n outcomes. Then we say x1 through xn is a sample of my underlying distribution. So to be more formally, we define a random sample from some distribution f, right, of length n as a set of x1, x2 to xn, which are RID, independent, identically distributed random variables with distribution f. And n here, which is the number of random variables you got, right, is called the sample size. So this is the definition of random sample. It's basically just some formal abstraction of doing random experiments repeatedly, doing repeated random experiment in practice. Suppose I flip a coin for 10 times, And so I got 10 outcomes, right? Each outcome essentially is a random variable. Now I look at these 10 random variables. I call this set of random variables as a random sample of my Bernoulli experiment that flips the coin. And the sample size is simply 10. Questions? Any question regarding the definition? Okay, great. So here are some kind of summary of what the random sample reflects. Okay, so a random sample represents an experiment where n independent measurements are taken. Okay, it's not only like you flip the coin. You can you're using your telescope to observe some data you record for 10 times. Right? And if you observe a set of particular values for this sample, right, x1 through xn, then we call the list of values you observed for x1 through xn as a realization. So usually we use lowercase letters to denote the realization of a random sample. So we use capital letters, x1, big X1 through big Xn, to represent the random sample itself. And their observed values are denoted by their lowercase version, x, like small x1 through small xn. Okay. So far, is everyone happy about definition? Any question? Any concern? Okay, great. So now we can define the so-called statistics. Right? So we mentioned that this discipline, named statistics, are actually talking about how you're going to summarize some information from the random sample, right? So what is the statistics itself? So statistics essentially is just a function of random variables. That's it. As we mentioned before, right? Random variable is a function. A function of random variable is also a function. It's also a random variable. So if we have a random sample, which essentially is just n RID random variables, x1 through xn, right? So a statistics on this random sample is actually a function of this n random variables. Say t, x1, x2, until xn. And this t can be arbitrary. You can define whatever function you like. And as long as it is a function of this n ID random variables, you can call it statistics. Sorry. So then the question is, what are the popular or commonly used statistics? Okay. So here we're going to give some example, which pretty much sure everyone has seen before. The first one is called the sample mean. So the sample mean is simply the average of this n random variables in the random sample. Another example is called sample variance. So sample variance is defined in this way. So you're going to first calculate the sample mean. So this x bar is simply the average of this n random variables in the random sample. And then you calculate this guy. So you're going to subtract each random variable by the sample mean, take the square, then add them all together, and then divide the sum by n minus 1. Right? Someone may question, why do you divide it by n minus 1? Right? That sounds a little weird. But this is kind of like a very well-known result because the sample variance is the unbiased estimate of the covariance, which we're gonna discuss later. But here we just show you some concrete case about statistics. Okay. So here we want to point it out. We want to ask. So is sample mean or sample variance a constant or a random variable? Any thought? Is sample mean or sample variance random? Or we can just simply view them as some kind of constant. Any guess? No guess. They are not constant. They are also random variables. So this is very, very important. Why do we see this, right? So this actually comes from the definition, right? So the random sample is defined as a set of IID random variables, right? And the statistics are simply a function of these n random variables. A function of random variables is still a random variable, right? So that means all statistics are random variables, including the sample mean and the sample variance. How do we see this, right? How do we see this from, I mean, not from the definition, but from more intuitive way? So because x1 to xn are random variables, that means if you collect the values, if you want to look it takes some measurements on those random variables, right? And this time you probably will say a set of values, say 0.1, 0.5, 0.9, right? And then you can calculate the value of statistics, say the average, maybe 0.45. However, if you do the next measurement over this n random variables, you probably get another set of values because they're random. So it could be 0.2, 0.2, 0.8, right? And then if you take average of them, you might get 0.4. So that means this sample mean could vary with the change of the values of the random sample. And the random sample, it's random in nature because whenever you do the experiment again, right, you might have you might observe a total different set of values, and then you do average or you calculate the sample variance, the value will change as well. That's why sample mean, sample variance, and all other statistics will change along the values of those random samples. So they are essentially random variables, not some constant value. Right? And understanding this point is extremely important because I think the final topic we're going to discuss in this class is about hypothesis testing, right? And the confidence intervals. And it is a very counterintuitive, at least when I was an undergrad student 20 years ago, I was confused about that. I spent quite a long time. I realized that, okay, the confidence intervals and those statistics are essentially random variables. And those true values are constant. You're actually using some random variables to estimate some truly ground truth constant, but without any random. Right? So if you don't understand this, then you will get confused when we talk about confidence intervals, hypothesis testing, all kinds of stuff. So just keep it in mind. Whenever we say, okay, we want to calculate sample mean, want to calculate sample variance, want to calculate median, we want to calculate first order, second order, and quantile, all those are statistics. That means they are essentially some kind of random variable. They can change when you redo your experiment. Any question? Okay, so let's rest for 5 minutes and then continue. Yeah, there probably will be some listed formula, but if there's not, that means you don't need to. I mean, we're not giving you the definition of expectation or the covariance. That's the basic, right? If you want you to calculate, say, the PDF, joint PDF for very Gaussian, of course, we're going to provide the formula. It's like a very fundamental. We're not providing that. Yeah. But for more advanced, as we mentioned, like you don't need to memorize that. And of course, if you need that, we'll provide you that. Okay, that sound good?
Yeah.
Okay. Okay. Hello, everyone. So let us continue. So as we mentioned, statistics is just a function of the random variables in a random sample, right? So that means statistics are essentially also a random variable. It could change along with the values of the random sample you get, right? Which we call realization, right? And when you do some kind of experiment, you collect the values, or the measurement of your random sample, you got the realization. And you evaluate your statistics T over this realization, you got some value for the statistics. But when you do the experiment again, you probably will get another set of values, which is a different realization. And then you calculate statistics again, you might get different value of a statistics. So just keep in mind the statistic itself is random variable. It could change, it could vary along repeated experiments. So we introduce two examples for the statistics. One is sample mean, one is sample variance. These two might be the most commonly used statistics. But here we want to give others. Okay. The third one is called median. So what is median? So you got this x1, x2 to xn, right? They're in random variables. And now I want to sort those random variables according to their values, such that I got x1 after sorted, right? I denote them as x1 prime less than or equal to x2 prime less than blah, 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 less than or equal to xn prime. Then I take the center element in this sorted list, which we call the median. So if n is odd, this is the center, right? If n is even, actually, you just check the two middle elements and just take the average. So this is called the median statistics. So the median statistics is often viewed as a more robust way to look into the average behavior and to reduce the bias. For example, if we look at the income, right, everybody, individual income, if a country, the biggest income is just got by very few people, right? And most of the people like just a much smaller income. If we do the average, you probably will be surprised. Okay, this average income of the whole nation is still very high, but that doesn't reflect the true wealth or the richness of the country, right? So in that case, people often use median. Namely, I just sort the incomes of the population, right? And then I look at what's the median income. That can reflect, okay, truly on average, most ordinary people, how much they will earn every year. Right? That can truly reflect the financial situation of the common people, right? So it's called median. Right? And sometimes, like, people are often interested in these so-called order statistics. Again, whereas these order statistics are still like after you do some kind of sorting, right? X1 prime less than or equal to x2 prime less than or equal to until xn prime, right? So someone might be interested in, okay, what's the smallest value? What's the smallest random variable? What's their distribution look like? Right? So this is called the first order statistics. what's the second order? Like second order, what's the biggest order? What's the second biggest or second smallest? So this kind of statistic is very important in auction. In online advertising companies like Meta, Google, they're all earn huge amount of money from this online advertising auction. And interestingly, they're the best auction strategy was known to not taking the one who gives you the biggest price. Instead, you always choose the second best price. And they have some like very strong theoretical justifications from gaming theory, from all kinds of theory, which we're not gonna discuss in our lecture. But this is an example showing that, okay, if you want to look at the property, right, what's the second best price, we'll distribute, right? We're gonna look at this order statistics. And another type of statistics is called empirical quantile. So what does it mean, right? So you can specify the proportion P, right? So P could be 0.1 or 0.9. It just means, okay, if you sort those random variables, right? X1, X2 through Xn, right? So you want to look at which random variable is at the P proportion of the data below. So basically, suppose let me suppose your n is equal to n is equal to 10, right? So your x1 through x10 is sorted, right? So you want to look at what is Q10 at 0.1, 0.2. That basically means you're going to choose x2. Why? Because below x2, you're gonna have x1, x2. It will take 0.2 portion of the total number of the data points. Okay, so that is called quantile. So probably you want to do 0.9. That means you're going to choose x9, right? Because all the points through x1 through x9, they're below x9, right? So that means 90% of the data points are below x9. So x9 will be the empirical quantile at 0.9. Question? Okay. And from the historical reason or academic reason, I mean, people also develop the so-called quartiles. What does quartiles? It just means you're going to choose P, the quantile, the empirical quantile with special values, with the 1/4 or 2/4 or 3/4 or 1. This is just why this is called quartiles. It's like that. It's a 1 quartile, 2 quartile, 3 quartile, 4 quartiles. Right. So, and based on quartiles, we can also define the statistics as the so-called inner quartile range. So basically, it just tells, okay, what's the difference between the two quartiles? For example, if you got 8 random variables, if you sorted them, right? X1, X2, X3, X6, X7, X8, right? So we know that the quartile of 1/4 will be X2, right? Because X1 and X2 are below X2, it takes 1/4 of the total number of data points. And we know that the quartile of 3/4 is x6, right? Why? Why x6 should be the 3/4 quartile? How many data points are below x6? Any thought? We're assuming x1 through x8. We got eight. We got 8 random variables, right? We're assuming they are sorted. Now we see that x6 should be the quartile at 3/4. Why? Yeah. Okay. So the basic reason is that if you choose x6, you see x1 until x6 are all below x6, right? So that means 6 out of 8 data points are below x6, which corresponds to a 3/4. Right? That's a quartile definition. And this is, I mean, it's a little bit uh, not straightforward. Okay? It just represents this 3/4, or this P just represents the proportion of the data points below that point. Right? So if you take x6, you say, okay, x1, x2 until x6, all less than or equal to x6. You got 6 data points below x6, right? You got 8 data points in total. So that means below x6 will be a 3/4 portion of the data points, right? That's why we know x6 will be the quartile at 3/4 or 75%. I mean, if you feel uncomfortable to this kind of concepts, that's totally okay. Because when I was an undergrad student, when I first look at those definitions, I feel weird as well. Right? It took me some time to really understand meaning, right? So, and then this inner quartile range is kind of go even further. That means like, okay, if I find out the quartile for say 0.75, which is x6, and then 0.25, which is x2, then I want to look at the difference between these two quartiles. I want to look at, okay, how far away from your 0.75 quartile and from 0.25 quartile. Right. This will be very useful when we do some kind of uncertainty quantification in the frequentist point of view. Okay, any question? We're probably gonna look at this, relook at the definition of quartiles, the inner quartile range, those kind of stuff when we talk about confidence intervals and hypothesis testing. But won't be the focus of this our lectures. So don't worry too much about that. But we just request everybody to try to understand the definition here. Okay, so again, a statistics, no matter defined in whatever form, it is just a function of the random sample, meaning that essentially statistics is also a random variable. It is not a fixed number. And the statistics, because it's a random variable, it also has some distribution. So if we perform an experiment, we have some realization of our sample. Okay? So by realization, it just means, okay, if we perform the experiments and look at the measurement of those x1 to xn, and we get the set of values denoted as this small lowercase x1 through xn, right? And then we plug in these numbers into the formula of our statistics and calculate the value, which we denoted as this lowercase t. We call this is a realization of the statistics. So basically, it's just an evaluation of the function for this statistics. Okay. So here's one concrete example. Suppose I do some experiment, say I flip the coin for 10 times, right? So I got a realization of my random sample, which will be just the sequence of 1 and zeros, right? 1, 0, 0, 1, 1, and 1, right? For example. So this is one realization of my random sample in my flipping coin experiment, right? Then I evaluate my statistics at my realization. I get some value. This value is called the realization of my statistics. And suppose my statistics is sample mean. That means I'm gonna just average the values in my realization. I got some value, which is my realization of the sample mean. Does it make sense? To be more concrete, probably, oops. To be more concrete, suppose I got a random sample of size 4, right? So this random sample consisting 4 ID random variables represent the outcome of my flipping coin for 4 times. So now, so now I want to perform an experiment. That means I just independently threw the coin for 4 times, and my observation of those values are 0, 1, 1, 0. So this is called a realization of my random sample, right? So I'm interested in using the so-called sample mean as my statistics. The sample mean is simply just the average of my random variables in my random sample, right? It's just x1 plus x2 plus x3 plus x4, right? So now, after doing one experiment, I got my realization of my 4 random variables, which are 0, 1, 1, 0, right? So now I just evaluate my sample mean from this realization, which gives 1/4, 0 plus 1 plus 1 plus 0, which is 0.5. So this 0.5 is called a realization of my sample mean statistics. Does it make sense? Any question? I hope everyone is super comfortable now. So now you can see, okay, how does this realization things look like, right? So of course, I will do another set of experiments, right? Which I have a different realization, which might be like 1, 1, 1, 0, right? So then I evaluate my sample mean statistics on this new realization. I got another realization of my sample mean, which is 1/4, 1 plus 1 plus 1 plus 0, which is 0.75, right? So you see that actually the sample mean its realization can change along with different experiments as well. So it is essentially a random variable. Any question now? Okay, great. So in statistical literature, we usually use uppercase to represent random variable and the lowercase to represent the realization of the random variable, meaning that, okay, if you just do the experiment and measure the value of random variable, this measured value is usually denoted by lowercase um, uh, letters. Okay. So, and in practice, we probably will see different statistic plots like histograms, empirical CDF, box plots, scatter plots. Those are based on the realization of the random variables. Right? So because this course won't cover the R language, so we won't show the examples of those guys. Right? Okay. So now we introduce the concept called sampling distribution. Given a sample which consists of n ID random variables, x1, x2 to xm, and each xi is a random variable, and all of them share the same probability density function. The statistics is defined as the function of this n random variables, right? As we emphasized repeatedly, the statistic t is also a random variable. So now that it's random variable, it should have its own probability density function, right? So the key point is here is that usually the distribution or the PDF of the statistics t is very different from the PDF of each individual random variable, say x1, x2, or xn. Why? Because t is a function of this n random variables, right? It kind of like aggregate all the information across these n random variables and do some kind of transformation. For example, you do average, or you do some variance calculation. You do some like a square, and summation, average, all kinds of stuff. Right? In some other more complex statistical definition, for example, the quantile stuff, right? So the transformation could be nonlinear, or even does not have any closed form. So that means the underlying PDF of the statistics could be very, very different from the random variables based on which they calculate the statistics. Any questions so far? And then we call the distribution which the statistics t follows as the sampling distribution of t. That's the definition of sampling distribution. So what's the usage of the sampling distribution? So at least theoretically, if we know the distribution of the statistics t, we can answer questions like, okay, what's the probability that t is in some range? Say, what's the probability your sample mean is between 0.5 and 0.6? Right, for example, you flip the coin for 10 times, you got sample mean, right? I want to know, okay, on average, your sample mean, what's the chance that your sample mean is between 0.49 and 0.54, right? And if that chance is very high, then probably I will believe, okay, your coin is very likely to be a balanced coin, right? A even, a very fair coin. how do we compute this? Any thought? How do you compute the probability between the probability that your statistics T is between A and B? Yes, exactly, right? You can use in CDF, you can use in PDF, right? So if you, as we mentioned, if you know the sampling distribution of T, and suppose their CDF is, I don't know, maybe we can use big F, right? Then this probability is just the CDF evaluated B subtracted by the CDF evaluated A, right? Okay. Or if you know the PDF, the probability density function for T, then you can do this through the integration, right? You integrate the probability density function of T in the range A and B, you get the probability. So let's look at some example. Suppose you're given a sample of size n, right? That means it consists of n IID random variables, x1, x2 to xm. And we know the expectation of each random variable xi is mu, and the variance of each xi is sigma squared. Then what do we know about the distribution of the sample mean? Sample mean, again, as we mentioned, is just the average of this n ID random variable. Right? So what do we know? What do we know about the distribution of the sample mean? Any thought? Or at least what kind of properties should we know from the sample mean? What's the expectation of the sample mean? Yes, exactly right. So first, if we look at the expectation of the sample mean, well, I'm gonna copy the definition here. If you look at the expectation of sample mean, you see that, again, leverage the linearity of the expectation. You know, you can put the factor, constant factor 1/n outside, and then sum over all the expectation of each xj, right? You know, each xj is expectation is mu, and you get the expectation is the same as the original random variables, which is mu. That's good, right? And what's the variance of the sample mean? It's similar. It's the same as sigma squared. Okay, that's a very, very good observation. Actually, the variance is shrink by a factor of it. The sample the mean of the variance of the sample mean is sigma squared O(n). Yeah, we'll get into that Thursday. Let's stop here today and see you on Thursday.